Greetings, everyone. Somebody today asked for some review on parametric equations, and I'm associating it with vectors because the most likely way you're going to see this on the AP exam would be, them in combination with each other. So I'm going to do this via an old AP question from 2009, and so this was an interesting question when I saw it back in 2009. I really liked it. But it requires a little bit of thought, and it's a good example of how they might try to get you with parametric and vectors. I don't mean try to get you in a bad way, but try to get you to use parametric equations and vectors in the AP. So we have this diver leaping from an edge of a diving board into a pool below. The figure above shows the initial position of the diver and her position at a later time. At time t seconds after she leaps, the horizontal distance from the edge of the platform to the diver's shoulders is given by x of t. And the vertical distance from the water surface to her shoulders is given by y of t, where x of t and y of t are measured in meters. Suppose that the diver's shoulder is 11.4 meters above the water, then she makes her leap, and when she makes, her shoulders are 11.4 meters above the water when she makes her leap, and that dx dt is 0.8 and dy dt is 3.6 minus 9.8 t. For a t between 0 and a, where a is the time the diver's shoulders enter the water. So in this, if you're looking at the data that they're giving us here, we have motion in 2 dimensions, and so we do need to describe this by a set of parametric equations or a vector. And so x being our horizontal displacement from where she started, y being the vertical displacement. But they're not giving us the functions for x of t and y of t. They're giving us the rates of change of those values, dx dt and dy dt, are their derivatives. So in other words, they're giving us the velocity vector, although they didn't write it as a vector, but because they're giving us dx dt and dy dt, these are the components of the velocity vector. And we have to, try to answer these questions. Now, I mentioned in class that when they do give us parametric equations or a vector, they're going to try to hook this back to some sort of one-dimensional motion case for just a moment. Even though the bigger picture here is in 2 dimensions, they're going to see if you can handle the one-dimensional question. And so if you look at what's happening here, Part A is going to ask you about the one-dimensional case. So it says they find the maximum vertical distance from the water surface to the diver's shoulders. Maximum vertical distance. We're trying to maximize y of t. We're trying to maximize the vertical distance. And so you should recall from the AB class that what we want to do is we want to take the derivative of y and set it equal to 0. So we want to figure out when dy dt is equal to 0. And so, well, they gave us dy dt, so that's 3.6 minus 9.8 t. So I can just go ahead and work from there. 3.6 minus 9.8 t. This is a calculator question, so they do expect you to use your calculator to help solve these things. And so when we do a little bit of rearrangement here, bring something over, divide by the 9.8 or negative 9.8, depending on how you set this up. So it's going to be 3.6 divided by 9.8 by the time you're done with this, which is some approximate value, which I'll write down in a moment. And there it is. Okay. Again, we're trying to find the maximum vertical distance. So, whenever we were last year, at least in the AB class, we talked about vertical motion. Another way to put this into context, we always said this was going to occur when the velocity was equal to 0. So when y prime is equal to 0. And so now we know the maximum is going to occur at this point. So what do we have to do? We have to figure out the y coordinate at this point, or the height at this point. So, well, we know that she starts a certain distance above the water already. So let's go back and see this for a moment. She starts 11.4 meters above the water. So her y value at this time, 0.36735 approximately, is going to be that 11.4 plus, like how I wrote 5 there, 11.4 plus the integral from 0 to 0.36735 of dy dt. with respect to dt. And for this, you're going to, we can work this out by hand. This is a simple polynomial. This is one that you just plug into the calculator and let the calculator do all the work for you. So let me go figure out that value. And there it is. So, don't bother to try to evaluate that by hand. Just get that one done, using the features of your calculator. All right, so let's go back and make sure we've answered all of part A. So find the maximum vertical distance from the water surface to the diver's shoulders. So everything's measured from the diver's shoulders, and so we're good to go on part A. And this is a 3-point question, by the way. Let me assign the values to this. I don't remember off the top of my head, but they did give it 3 points. Now they want us to find the time A, or find A, the time the diver's shoulder enters the water. Okay, so, well, what do we want to do for that one? Well, we got to think of the vertical distance traveled, okay, or at least the vertical position at some time. So we're looking for y of A. We want to know what the vertical position is at time A. That's the time when the diver hits the water. So this looks almost identical to what we just did. We're going to have, the height 11.4 plus the definite integral from 0 to A of this, vertical velocity here, dy dt dt with respect to dt. And we want to figure out when that is equal to 0. When the diver hits the water, then she's 0. When her shoulders hit the water, her shoulders are 0 feet above the water surface. So, fundamental theorem here happening again. So we have our initial velocity value, initial position value here, 11.4, plus the displacement between 0 and A. We want that to equal the height at that moment when, at 0 when it hits the water, when she hits the water. So that's going to be 11.4 plus. Now, if you think about taking the antiderivative of dy dt, so we're going to get 3.6t minus 9.8 over 2t squared. So 3.6 t minus 9.8 over 2t squared. We would need to evaluate that from 0 to A and set that equal to 0. All right, just double checking my arithmetic here. All right, I do have one little error here that I want to fix before I continue on, and that is that 11.4 is not part of the integral. And so let me move in my my brackets to here for a moment. So then this becomes 11.4 plus 3.6 times A minus 4.9, 9.8 divided by 2, A squared equals 0. And now, calculate a portion of the test, you can just go ahead and solve for this value, and you get a value that I better go look up because I don't remember it. And there it is, 1.936. Remember to correct it later. Switching screens to write it down. All right, so now we know the time that it takes for her to hit the water, her shoulders hit the water. Part C says, find the total distance traveled by the diver's shoulders from the time she leaps from the platform until the time her shoulders enter the water. All right, total distance traveled for parametric equations, that's like our arc length for parametric equations for vectors. And so our total distance, just to remind you of this, is going to be the definite integral from A to B of the square root of x prime of t quantity squared plus y prime of t quantity squared with respect to t. That dt is on the outside of the square root symbol. Apologize for the sloppiness of that a little bit. Well, total distance from when she dives until she hits the water, let's make some room over here. So we know she hits the water at that time, A, that 1.936, but I'm going to use the letter A when I write this down. It's a little cleaner. And then what do I need here? Well, they gave me x prime, that's dx over dt. That's 0.8. And so I'm going to have 0.8 squared plus, and then we had 3.6 minus 9.8t, quantity squared, dt. There's our total distance. And now I just got to plug that into the calculator again, let the calculator do the heavy lifting and get the answer. And there's our answer, 12.946. So a simple total distance question, using arc length for parametric equations, using the integral of the speed, which is the integral of the magnitude of the velocity, which, the magnitude of velocity we found with the Pythagorean theorem. Fairly straightforward. One more question for this one. Find the angle theta, where theta is between 0 and pi over 2, between the path of the diver and the water at the instant the diver's shoulders enter the water. What they're trying to get you to envision here is slope in parametric form, okay? And so when the diver, I'm not going to try to draw the diver, but let's say the water's here, and the diver's this stick-looking figure here. I'm looking for the angle here that with which the diver enters the water. And so I need a couple things here. I need to think of slope, like I just mentioned, and then I'm going to have to go back and use a little bit of geometry from something hopefully you remember, a little basic trig, if you want to look at it that way. So how do we find slope in parametric form? So you look at dy over dx is equal to dy over dt divided by dx over dt. And we want to do this when the diver hits the water. So, you can put this little vertical bar here, and you put when t is equal to a. And all that means is you're going to take a and plug it into dy over dt, and then plug it into dx over dt and get the answer. And if you do this, you get negative 19 point, I already forgot it. There it is, negative 19.21913. And so now we have to use that value to figure out the angle, okay? We just calculated the slope, okay? So basically we've worked on the rise over the run here, okay? And so, going back to some basic geometry here, we've worked out, okay, essentially y, over x, or change in y over change in x over here like this, but we want the angle measure. So how would I find the angle measure? That's right, inverse tangent. I know you were thinking that. So I'm going to need the inverse tangent, and with this one here, I don't want to use the negative 19.21, what did I say it was, 21913. I want to use the positive value. This goes back to some properties of the inverse trig functions. Inverse tangent is defined for values within the first and fourth quadrants, okay, between negative pi over 2 and pi over 2 exclusive. And so if I put in the negative 19.2193, I'm not going to get an angle between 0 and pi over 2. I'm going to get an angle between negative pi over 2 and 0. And so that's not what they said. If you go back to the question way back over here, they said they want theta to be between 0 and pi over 2. And so if I use the negative, then I'm not going to end up with the angle that is in the interval that they want. So I have to use the positive because I want the first quadrant angle and not the fourth quadrant angle. So plug that into your calculator and see what comes out. And you should get 1.518 or 1.519. I'm using these solutions. the scoring guide for this. So the truncated answer 1.518 or the rounded answer 1.519. They'd accept either one. You don't have to put both. Just put one of them down. Note that these are radian measures. Okay, so it may look a little bit odd, but it's that's what it is. It's a radian measure, and not a degree measure, and so it might look a little bit different. Like you might think of that number as seeming a little counterintuitive, but remember the first quadrant is between 0 and pi over 2, and pi over 2 is a little bit more than 1.57, and so this is less. These numbers are less than 1.57, so it is in the first quadrant. Okay, I hope that was an instructive and helpful example. Go study if you want, or go relax.